Okay, picking up where we left off. We're just going to talk about scattering light. So, light waves reflect, as we were just talking about, at the same angle that they're coming in at. Boing, 90 degrees. They bounce off at 90 degrees. So, to scatter light, all you need is a less than flat mirror surface or any reflective surface, anything that bounces the light around. And at a microscopic level, it looks something like this. So the light waves, which are extremely small, I made a correction to myself. It's not 7/1000ths of a millimeter, but 0.7 thousandths of a millimeter for the red light, and 0.4. So between 0.4 thousandths and 0.7 thousandths of a millimeter. So these tiny little waves are hitting and bouncing and moving about in different directions because they come in, and each one, it's just that they're just because it's not hitting a flat surface, and so it bounces kind of all over the place. The result is that the light gets diffused, and this kind of goes back to shadows. I'm going to jump back to the shadow slide really quick. That if you have a concentrated light source, you're just going to have a very dark shadow. This isn't the great example here because it would be better to just look at a single object. But if you had a concentrated light source, you would just have a sharp shadow with distinct lines. The penumbra is light that it's not that it's light that got around a bit. You know, some of the light getting around because it's more of a diffuse source. So here's a sharp source and here's a diffuse source where the light's coming from many different angles. And in photography, it's common to use a light diffuser. And so here's direct flash picture and with a flash diffuser. So this is a professional camera, and you can. This is just the white light diffuser, but you can change the color of the light a little bit. Well, it looks like they did actually. Maybe they put that yellow light over the flash. The colors do look a little different. Look at the wall. So here's just the direct flash, and then adding the diffuser to it, you see you get rid of that harsh shadow altogether because the light's coming from many more different angles, and that's a nice little piece of equipment if you can stick that onto your camera. Mirrors don't have to be flat. They can be concave or convex. Now concave is, think of a cave, it goes inwardly. So a concave is, there's an inward scoop to it. Biconcave would be kind of like that. It's scooped in on each side. Or it could be convex. This would be a biconvex. So, and this could be for a mirror or for a lens. Right? You can shape glass, grind it, and so you could have concave mirrors, concave lenses, convex lenses, and it's going to have interesting effects because of how the light bounces off or goes through it. So concave mirrors, the light's bouncing, it's kind of a parabola effect here. There's a focal point, and so a slight curve is great for magnification. So think of like a makeup mirror right here, where it's it's a very slight curve to it, but it gives a nice magnification. Now, if you are back far enough, the image gets flipped upside down. Gets flipped upside down because look, the light that's coming in from the top is going to end up going down at the bottom, and the light coming in the bottom is going to end up at the top. And so if you're looking at it from past the focal point, it's not going to be magnified, it's going to be upside down. Well, it still can be magnified, but it will be upside down. You could also, an interesting thing, you could do it the other way around, where there's a light source here and it will bounce. So these arrows think of these arrows going the other direction. So the light bouncing here to the mirror and then out this way, bouncing here to the mirror, out that way, bouncing. So this light source can be concentrated, and a good example of that is your car headlight. Go look at your car headlight. You'll see that that there is a concave mirror, and that the light bulb is just out in front of it, and the light bulb is going to shine at that focal point, so that instead of just a light bulb and spreading out the way it normally would, is bouncing off that mirror. Sure, it's spreading out in all directions to the front, but it's coming out as a straight beam because of how this parabola works, this parabolic mirror works. And so the light's bouncing here and going straight out, so you get these nice straight lines coming out of your headlight. So slight concavity is, for magnification, like that makeup lens. A deeper concavity would be the headlight of your car, as an example. Here's an interesting biconcave lens with a hole in it that is a fun little, it's called the miroscope, or excuse me, excuse me. This is a fun little trick. You can put an object in the bottom of this and it looks like it's floating right above it. So you can put like a little toy down here and it looks like it's floating just above it. And you can, kids will try to grab it and they can't grab it. It's not there. And so what's happening? The light that comes in bounces off, down, out like this. So you're bouncing off of this concave mirror down to this one, and boom, here's the focal point for it. And so it's quite a great illusion. These are pretty cheap. You could have one in your classroom, and it'd be pretty fun because it will look like the object's there, but you can't touch it. You can put a quarter or a little toy or whatever. So that's fun. Another thing you can do with deep concave lenses, this parabola, is to heat things up from the sun. And so here these guys are out, I don't know, camping, bike riding, but they've got a big parabolic mirror here, which is just a concave mirror, and they've got the cooking pot at the focal point. And that's going to get very, very hot. You can easily light a piece of wood on fire with one of these lenses. So if you look for parabolic mirrors, you can see examples of people doing that. This whole trough is the same idea. It's got a pipe right at the focal point, and this is going to track the sun. It's going to tilt during the day, and this is a form of generating electricity from the sun. These are not solar panels. These are just mirrors, and so it's not photoelectric panel. It is just a parabola that heats up a liquid that's running in this pipe. See the pipe going down the middle of the trough? So it heats up this liquid, and the liquid goes underground super hot and goes to a big pit of salt, and it superheats the salt because that's not going to burn. And then they run pipes, just water pipes, I think, through the salt, and it just instantly turns to steam. As soon as you have steam, then you can create pressure to drive a turbine and generate electricity. So we're not going to talk about generating electricity, but that's just another application of a concave lens. Okay, convex mirror, okay, curved outward. You're going to have a greater field of vision. So when you look at your right side rear view mirror, and it says objects in mirror may be closer than they appear, it's a little bit convex. That mirror's bulging out a little bit. Now, if you want a better view, you might buy those more convex mirrors. The little ones that you stick onto your mirrors, the little round one, to give an even greater view of what's around you. And the little safety mirrors that they have in stores, or when you need to kind of see around a corner, That's when you'd see these convex mirrors. And looking for pictures, a fun one that I found was M.C. Escher's print, Hand with Reflecting Sphere. So this is a good example of a convex mirror. So you can see how he's able to see almost 360 degrees around him with this very convex mirror. It's a whole ball, but it's acting as a convex mirror. And he gets this nice view, fisheye view of everything around him. Okay, images in convex mirrors are going to be smaller. So, here's his whole body fitting in there. Here's his hand up close, and you can see things just get progressively smaller as you get further away. And if you have a shiny bowl at home, shiny mixing bowl or something, you can play with this same idea. So here's the person looking into the convex mirror, and the light coming in bounces in that fashion. Well, anyway, I don't know if this is a helpful illustration or not, but this is what he sees, and it's smaller than him. Now this is back to the concave mirror, the makeup mirror sort of thing, where the light, I don't know how to explain it well using this picture, but it's magnified. And the funny thing, if he stepped back further, so this is the person, this is the image he's seen. If he stepped back further, he'd be upside down looking in the concave mirror if he stepped past the focal point. Yeah, I don't know if I like that picture or not. I can't explain it very well. Refraction is how light waves get bent. So light travels in straight lines, but when it's traveling through one substance and hits another substance, it may take a bend. It'll still go in a straight line through that substance, but at a different angle. It gets bent a little bit as it passes through something. And we've all seen this with straws and spoons and things. So in other words, the light traveling through the air has a different refraction index than the water. And so when it hits the water, it bends a little differently. So it looks like the straw has shifted or the spoon is broken. So that bending of light is called refraction. And this becomes an issue a little bit with microscopy. If you're looking at something through a microscope, your slide is glass, your lens is glass, but there's a little bit of air between your slide and your microscope lens. And at high magnifications, this refraction is a problem. And so at the highest magnification, you'll put a drop of oil on your slide, and you have a big lens called the oil immersion lens. It touches the oil, and so instead of air being between the glass and the lens, it's just oil. And the reason for that is that oil has the same refraction index as glass, and so the light is going to pass through in a straight line and give a clear image at high magnification. So here's the light. It hits the glass, takes a bend, and then it hits the air again, and it's traveling, the same angle as it was before, but it's been shifted. As light rays pass into a less dense material, they bend outward, and they bend inward as they pass to a more dense material. So the glass is more dense, it bends in, and then it bends out when it hits the air again. I saw a better picture of that someplace, and I didn't include it, sorry. Okay, lenses. If you just have a piece of glass, things don't look different when you're just looking outside. So the glass and the air aren't that different. I mentioned with a microscope it makes an issue, but you don't see a lot of refraction just looking through your window. But you can also shape glass to make lenses, convex or concave, and this is going to be important for correcting eyesight, shifting a little bit how the light hits the eye. And I think concave is for myopia and convex is for farsightedness, I think. Sorry, I should have looked that one up. But the light rays are going to pass through the lens. They're going to bend towards the thickest part of the lens. So here they're going to bend inward, and here they're going to bend outward, kind of. So this is a better picture of that. So passing through this biconvex lens, they bend inwardly. And here, yes, they're bending more. They come and they bend outward. So basically, when you prescription lenses, which I'm glad that I've never had to wear it so far. I'm lucky that way. But prescription lenses, you can't. The focal point is the back of your retina, and if your eye is a little too long, the focal point hits right in front of your retina, and so things are blurry. And so by changing the direction of the light a little bit before it hits the lens, you can just refocus it to the back of the retina. I'll maybe put in the comments a link to something that explains that better than I just did. But you can imagine other uses for this as well. A magnifying lens is going to be biconvex and bring things to that focal point. So on the one hand, if you're looking through the magnifying lens at something, if it's right at the focal point, the light is, the image is going to be enlarged. On the other hand, if you're trying to pass sunlight through here, you're focusing it, and you can start a fire with that magnifying lens. A biconcave lens, if you had a little magnifying glass, but it was biconcave, it would actually make things look much smaller. So if you wanted to look at a painting and you wondered, well, would this look good as a stamp? Well, you could walk clear across the room so you could see it from far away, or you could stand close and look through a biconcave lens and see it as small. That'd be weird, but they do have such things. There's another thing that these concave lenses are used for, and I've never tried this yet. I'm anxious to. Google Cardboard. You can. This is a cardboard virtual reality. So it has, I think, some biconcave lenses in it. And what it is these images are offset slightly. It's just it's like those old stereoscopic viewers, that gives you the 3D effect. But you can have pictures and games and videos that are in 3D with Google Cardboard. And if you have an Android phone, this works very well. If you have an iPhone, you can still make it work. It still works, although it is designed for Android and whatnot. I should just figure out. I need to get one of these and try it. I mean, there are instructions to build your own. I would probably just, rather than build my own and buy the lenses, I would probably just buy a kit that already has the lenses in it. But looks like fun. There's the biconvex lenses for magnifying, a magnifying glass. There are several lenses in modern microscopes, but the objective lens is an important biconvex lens. Okay, light from the sun is white light, or white. When you see white light, and I'm looking up my lights in the room, they appear white. It is a combination of different wavelengths, and if you can separate those wavelengths out, then you'll get the colors of the rainbow. Roigbiv. Red, orange, yellow, green, blue, indigo, violet. I don't know what to say between indigo and violet, but colors of the rainbow, Roig-biv. You can look. People don't always draw their rainbows correctly, and you can get after them. But that's the order that they go in, because they're different wavelengths, and when they pass through the prism, they act differently. So Roig-biv, red, orange, yellow, green, blue, Roig, indigo, violet, and then we have ultraviolet. You know what I learned that I didn't know? The Renaissance artist Claude Monet, he had cataracts, and I think I did know that, and his eyesight got worse and worse, and so his paintings get more and more blobby as he gets older. But they got so bad, and they were filtering out, the cataracts were filtering out the colors, and then it was pretty much only seen in yellows, and he got so frustrated with it that he had his lens removed. And this is before they had replacement lenses. Nowadays, you get cataracts, you just get a replacement plastic lens and you're good to go. But he just had his lens removed. And the interesting thing is that we don't see ultraviolet light because our lens filters out UV rays. And so by having his lens removed, and he didn't have a plastic one put in, he actually saw in the ultraviolet range. And so things were much bluer, much more violety than other humans see them. So he was seeing like like many insects do, and some birds and so forth. He was seeing a broader spectrum, which was pretty cool. Anyhow, so you can see that the shorter wavelengths are going to bend more than the longer wavelengths as they pass through the prism. So here comes the white light in, and here's our Roig-biv. Red, orange, yellow, green, Roig-biv, blue, indigo, violet. So, and some people have more color receptors than other people, and women tend to do this more than men, differentiate, colors to a fine degree. Okay, colored light. This isn't the greatest example because that white doesn't look too white there. But you can have a blue light, a green light, and a red light, and you add them together, you add all of them together, you'll get white. Or you add blue and green light together, you'll get cyan. Blue and red, you'll get magenta. Blue and green, red and green, you'll get yellow. As you add the lights together. So adding light together to get these secondary colors is kind of confusing because it's really different than when you work with pigments, right? So this is quite a bit different than working with pigments, than mixing paints. What do you get when you mix paints? Well, if you mix the primary colors of cyan, magenta, yellow, you're going to get black. Cyan is this, bluish green, greenish blue. And mixed with magenta, you get regular blue. So, usually with your paints, you get red, green, and blue, and you mix colors from those. These are actually secondary colors. Your primary colors are cyan, magenta, and yellow. And CMY and black is K. If you look at your printer ink, you'll see CMYK for cyan, magenta, yellow, and black. Subtractive primary colors. Okay, sorry. Yeah, so you have to subtract. If you have blue, you have to get rid of the magenta to get cyan. If you have blue, no. Yeah, you're going to get cyan. If you get rid of the cyan, you'll get magenta. Well, it's still mixed with red. Oh, man. I'm confusing myself, folks. hopefully I'm not going to go further, because when I start to confuse myself, I know I'm going to confuse somebody else. And I like to mix paints, so I shouldn't confuse myself here. Okay, I'll try this again. Paintings are about absorbing the colors that we don't want from the white light around us. So blue paint is blue because it absorbs all the spectrum except for blue, and it's reflecting that blue light. Black, my shirt's black, it's absorbing the full spectrum and not really reflecting much back. So magenta is, something that's magenta in color. It's absorbing everything but the magenta. Why is the sky blue? Because blue is a high energy wavelength, high frequency, high energy wavelength, and it gets easily scattered by hitting oxygen and hydrogen and water molecules, these different molecules that are in the atmosphere, and so it gets scattered, less of the blue coming down to the earth, and more of it, it gets scattered into the sky, going out different directions, and so we see it. We see that blue light up there, and it still comes down to us also. We do get blue light, otherwise we wouldn't see anything blue, but it gets scattered. Oh, an interesting thing to think about, green is the color of plants. Plant leaves are green. They are reflecting the green. That means they're absorbing red and blue and yellow. They are absorbing those colors. So the colors that plants need to grow are the red, the blue, the yellow. What they don't grow well under is green. If you put a plant in green light, two things. If you had a plant in a room and you just put a green filter over your light, so only the green light came through, two interesting things. One, the plant would look black, and two, it wouldn't grow. It doesn't grow under the green light. Okay, on hazy days, longer wavelengths are also scattered about. So if there's a lot of smoke or dust or pollution, it just kind of looks gray, because you get all different colors scattered about in the atmosphere. At sunrise and sunset, it's got more atmosphere to pass through because it's coming at a low angle, and so most of the blue gets filtered out. I said that plenty of blue light comes to the planet. Well, at sunset or sunrise, less blue light comes, and so we see those lower frequency reds, yellows, and oranges more brilliantly because the blue's been filtered out. If you look at water, you say, why is the water blue? Well, it depends a little bit. If you're just looking down at it, it's probably just a reflection of the sky, right? The water is usually the color of the sky, for the most part. And, if we're talking deep water here. So the deep blue sea, it looks real blue because it's reflecting the sky. It's just a big reflection here, really. But if you're under the water, the red light gets filtered out by the water. And so you get this nice cyan color, this bluish green cyan color that's left. It's because the red's getting filtered out. Okay, we're going to stop there. And there are lots of fun little experiments you can do in your classroom with light and lasers and I don't know, just fun. The book has a few activities. You can come up with more looking for your own online, but easy to experiment with light and to do some cool stuff. All right, hope that helps, and hopefully, I apologize if I caused any more confusion, but hopefully helped. Thanks. Bye for now.